Okay, can you hear me now?
Yes.
Okay, and do you have background noise because it is warm in here and I've got the AC running, but I don't want to have that white noise on the bothering everyone.
There's no noise, so
Perfect.
Yeah. Great.
All right. So thank you very much for the lovely introduction, and thank you everybody for the great talks before. And I'm going to take ask a slightly different question here. Namely, I'm interested not necessarily so much in the training dynamics, but in the hypothesis class for deep and very wide multi-layer networks, and then the relation to training dynamics eventually. But so I'm going to talk first about the continuous approach to machine learning, and in relation to that, possibly what is often described as the mean field regime. And then we're going to talk about approximation properties of deep ReLU or multi-layer ReLU networks, which become very wide. I'm going to talk about at least two different concepts, one of which is related to the neuronal embeddings that we've seen in the previous talk. And then I'm going to briefly talk about the training dynamics to see how these function spaces are suited not only to approximation and learning theory, but also for training, because I think different things happen depending on what you look at. So let's talk about the continuous approach to machine learning. And this is following the philosophy that was started by Ima and Wu in 2019. So let us think about machine learning like we think about numerical analysis. So let's assume that we see two time-stepping algorithms. Xt plus 1 is xt plus something, and then we've got two different algorithms. And if we want to study both of those algorithms, then the crucial thing to realize is that both of them are discrete solvers for the same ODE. So once we've got explicit Euler and once we've got a higher order Runge-Kutta scheme. But if we want to understand what these do, what we really should look at is the limit as h goes to 0. And then we see that both of them are just different discretizations of the same problem. And realizing that and understanding the continuous problem, we can then go back and look at the properties of different numerical methods. So historically, machine learning has often been driven by, well, we've got a finite set of parameters, we've got a finite set of data points, and we optimize for them, and then maybe we look at the generalization error. But what I propose we can do instead is think about continuous problems and then think about different discretizations, which may be neural networks. But then the big question to ask is, what are the correct function spaces? How do we represent functions? And what are good continuous problems? And then in a second step, we can ask, are the neural networks, are the discretizations that we look at currently really the best we can do? And so the questions that we'll ask is now is, let's look at a hypothesis class, and then typically we've got the universal approximation property, but we may require very many weights, we may require very large weights. These functions may be extremely hard to learn, so I'm going to talk about function spaces in the sense of classes which can be approximated well by certain functions, which is very much in the spirit of the classical theory, where we've got a space, for example, of polynomials, and then we put a norm on that and ask how well can certain functions be approximated by that. And depending on which norm we put on them, we get Bezoff spaces, we get Hölder spaces, Sobolev spaces. So that is how we see those classical function spaces. And now we've got a different class of basis functions, namely we start from finite neural networks instead of from polynomials. And this viewpoint leads us to very similar considerations as the mean field regime, but it is a different philosophy. So in the mean field limit. Typically, we think of large systems of interacting particles, and in the mean field limit, the interaction between distinct particles becomes a distinction with ensemble averages, whereas here we just start from a continuous problem and then discretize. And I think for two-layer neural networks, the mean field terminology is very justifiable because we've got these distinct particles, we've got this Wasserstein picture, but in higher dimensional, deeper neural networks, we've got a very complicated index structure, and we've got these cross connections between all these nodes in different layers. So except for IID initialization, where everything seems to simplify considerably, I think the continuous approach is a better terminology. But then we need, if we want to follow this philosophy, we need to understand functions, we need to understand function representation, function approximation. So let's start by approximation theory. And I'm going to talk briefly about neural networks and neural trees, mostly because neural networks have a very complicated interaction structure. But if we look at a finite neural network, we see that basically we've got a coupling of two-dimensional index sets here and here. Well, we can just rearrange the index set into being a three-dimensional one. And then here we have to repeat one index that previously was only listed once. We have to list explicitly a couple of times, so that this rearrangement leads to redundancy. Whereas if we go the opposite way, we start with a three-dimensional index set and we rearrange it into a two-dimensional index set, then here we need to make this middle index set larger, and that leads to many trivial branches. So it leads to a different index structure, but we can, if we don't constrain the number of elements per layer, then the space of neural networks and the space of neural trees is exactly the same. And we are here going to look at infinite width limits. So there is no real constraint on the number of elements per layer, and no real constraint on the index structure by that logic. Instead, we are going to look at the path norm, which is a useful regularity criterion, which controls generalization properties, for example. And essentially what we do, if we've got a neural network on the left side of the screen, then we just multiply all the ways, take the absolute value and sum over them. And if we've got a neural tree, then we do the same, just the index structure is slightly different. Obviously, in the case that we've got only one hidden layer, both of them are the same. So if we just look at the path norm as a constraint, then this does not constrain the arrangement or the number of non-zero elements. So we may work for a while at least with the tree description instead of the network description, because that will be a bit easier to handle for us now. And later in the talk, when we talk about optimization, there it makes a huge difference, obviously, and then we will need to talk about networks in the classical sense. So let us introduce those function spaces. I'm looking at a compact set in RD, that is where my data lives, and I look at a Banach space of functions Z, which is a subspace of the space of Lipschitz continuous functions on this data set. And we are going to look at the closed unit ball in this space, and we make the additional assumption that it is closed in a weaker topology, namely in the uniform topology on K. And that is going to give us some nice properties, because then I can, if the closed unit ball in the Z topology is also C0 closed, then because it embeds into the space of Lipschitz functions and it is a closed set, the Arzelà-Ascoli theorem tells us that the closed unit ball in Z is compact in the C0 topology, and then we've got a compact measure space, and we can very, very easily apply a lot of results from measure theory, which otherwise would require more in-depth discussion. So for this, I'm going to look at mu being a signed radon measure, and we take a function g in the unit ball of z, apply the nonlinearity, and then compute this measure integral. That's a Bochner integral or a pointwise Lebesgue integral. And this represents a function. So I'm going to do the example first. If z is the space of affine functions from Rd to the real line, then this is just f of x is the integral over, well, we have some affine function here. We apply the nonlinearity, and then we take this integral, which is one possible description for multi-layer networks. The first I've seen it is Francis Bach in 2017, but it is one of the many, many versions of how to describe infinitely wide infinitely wide networks with one hidden layer. And we then define this norm to be the infimum over the measure, over the total variation norm of all measures mu, which induce the same function f mu, which is because obviously the map from weights to realization of a neural network is very much non-injective. So we need to take this infimum to factor out all the different sets of weights which give us the same realization. And then we get a function space of all functions which can be represented this way. The nice thing is, and the reason why I say this is set this up a little bit more abstractly than in the classical picture, is that this space of functions which can be represented in this way, it has the exact same properties that I assumed from Z. So this new space embeds continuously into the space of Lipschitz functions. Its closed unit ball is again closed in C0. It is a Banach space, and thus we can later iterate this procedure. So this is why I'm saying the tree index picture is a little bit easier for us right now, because we can just use induction, and then we get everything that we want just by iterating through it a bunch of times. So Z embeds into BZK, and this is, and the norm in ZK is smaller than 2 times the Z norm of F. And for that, I wanted to present the proof just to get a little bit of feeling for what objects I want to be working with. So we've got f of x is equal to ReLU of f of x minus ReLU of minus f of x. And then we can just use the homogeneity of the function. We pull this norm out once, have sigma here applied to this, and this can just be written as a measure integral where the measure is given by 2 deltas. And I wanted to have the unit ball in Z because I wanted to have a compact set. So I'm using this measure picture instead of some more classical descriptions. But I think this shows what we are doing to the functions. It also shows that a lot of what I'm going to be talking about is fairly specific to ReLU. So if we take a different activation function which does not have this homogeneity, then we really need to consider measures on function spaces possibly, and that is not going to be nearly as nice because we are lacking compactness. So let's stick with homogeneous activation functions for the moment. So we've got the same properties for BZK as we had for Z, and we've got a nice property in terms of the Rademacher complexity, which is proved exactly like you would prove the usual Rademacher complexity estimates for two-layer neural networks, which just derive from the complexity estimates for Rademacher complexity for affine functions on the same space. So a lot of the same, basically this is a way of reducing understanding multi-layer networks to understanding two-layer networks. And as two examples, if Z is the space of affine functions, then BZK is Barron space, which is the same space that we looked at before and a fairly well-studied object at this point. But on the other hand, if Z is just the space of Lipschitz functions on K, then BZK is just Z again. So we've got a very wide class of objects that we can be looking at here. All right, so this is an abstract setup. And now let's consider the following family of spaces. First, we look at 0 hidden layers. That is just the space of affine functions from Rd to R. And we look at the restriction of those functions to K, obviously. And then we just introduce those things recursively. So instead of taking an integral over sigma applied to an affine function, then we take sigma applied to a neural network infinitely wide with one hidden layer, and then so on and so on and so on. So we are just building up from 0 to 1 to 2 to 3 layers by recursion, which is again related to trees. But because for finite networks, the index structure of a tree and it can be rearranged into the index structure of a network and vice versa. If we've got a finite width neural network, then it is immediately inside this multi-layer space, and we can estimate the multi-layer norm just by what we call the path norm proxy. And again, the path norm proxy becomes a path norm if we take the infimum over all weights describing the same function. By the way, if there are any questions, please interrupt me. I'm not looking at the chat, obviously. So we can embed all finite networks. And why am I studying things with this path norm? It is mostly because the path norm is useful from the perspective of learning theory. It's a good norm to put on a space of neural networks because A, it's very easy to calculate if we know the weights. Well, maybe not calculate because of the infimum, but it is very easy to bound from above. And it has this nice property that if we look at a sample set with n elements inside this unit cube, and our hypothesis class, the model that we are training, lives in the closed unit ball of multi-layer space, then we can bound the Rademacher complexity in the L layer space by something that does not grow particularly quickly in input dimension, and we divide by square root n here, so we get a Monte Carlo decay rate. And the factor 2 to the L here can be reduced in terms of L if we look at slightly different path type norms, where we need some balancing conditions between the coefficients in different layers by Barron and Klosowski. So this dependency can be reduced, but mostly let's look at 3, 4, 5 layers, and then that is not what's going to kill us. The input dimension is with high likelihood, much more decisive than this little L. And the Rademacher complexity is useful because it bounds the generalization gap. So if we look at a functional, which is, let's say that this is our risk functional, this is what we want to reduce. We have an H, which is in the hypothesis class. and we want to minimize an integral of loss, which depends on h of x and some unknown labels y. But instead, we have IID samples from the distribution P, but we do not have direct access to the distribution. Well, then this Rademacher complexity bound tells us that the discrepancy between what we are minimizing in practice and what we want to minimize is not particularly large. Well, it goes to 0 as square root n with a high probability over the choice of samples. And these multi-layer spaces get their good properties directly from the previous generalized Barron spaces. So we know that multi-layer space is a space of that the path norm on multi-layer space dominates the Lipschitz norm of a function. We know that the closed unit ball is C0 closed. We know that it's a Banach space. Then before I showed you that WL minus 1 has to embed into WL with a factor of 2. So a priori, that looks like we might pick up an exponential dependence again, but we can get rid of this, and for little l smaller than capital L, that's really just the factor of 2, not 2 to the L minus L, because for positive function, by just taking the positive part, the factor 2 disappears, and so we only pick it up once. And obviously, because of the universal approximation theorem, multi-layer space is C0 dense for any depth capital L. We've also got the property that if we've got a function with capital L layers, which is vector valued, and then from the image of that function, we've got a network with little l hidden layers, then the composition can be represented by capital L plus little l hidden layers. And we get nice norm bounds for this composition. So I told you that this is a good norm, but is this really the correct function space to be considering? Because we are using a tree index structure, not a network index structure. So are we considering something that is too large? And first of all, we've got a compactness theorem, which says essentially that multi-layer space embeds compactly into good function spaces. And as an inverse of approximation theorem, this is a closedness condition. So if we look at a sequence of, say, finite neural networks, which converge to something in L1, and we know that their path norm proxies remain bounded, then we can show that the limit is again in this multi-layer space, and the limit satisfies a good norm bound. So all finite neural networks and all of their limiting objects, even in weak topologies under suitable norm bounds, are inside our space. And conversely, we've got a direct approximation theorem saying that if we look at a function in multi-layer space, we've got L hidden layers, we choose some M, then there exists a finite neural network with L layers such that we can define the sequence of functions and such that we get convergence of Fm to F in the L2 topology. We get a convergence rate of m to the minus 1/2, and we can bound the path norm proxies by the intended norm of the limiting function.
Hi, Stephan.
Hi.
There are two questions in the chat.
Okay.
And one is, what is the dependence of the Rademacher complexity on the radius of the ball?
So the radius of the, so we've got this this cube in our data space, and there that enters linearly, and also the norm of the path norm, the multi-layer norm, enters linearly as well, because for Rademacher complexity, you've got this sum in which h enters linearly, so you can just pull a constant out.
Okay, and thanks. And the second is, can one see the advantage of multi-layer compared with two-layer from these results?
I will show something later, but I think there is a lot to be still done. There are some results on depth separation, and I'm going to show some, we proved in a different article, a structure result for two-layer functions, which actually helps you to show that a lot of functions cannot be represented exactly as with a two-layer neural network, even if the width becomes infinite, as long as the norm remains nicely bounded. So I think that function representation is an important tool, and I think there is a lot of work to be done, but I think that it's possible to go into this direction, absolutely.
Okay, thank you.
Right, so we've proved that the multi-layer spaces are large enough. This is more in the spirit to show that the multi-layer space is not too large. Namely, we say that every multi-layer function can be approximated by finite neural networks to the precision that we want under good norm bounds. The problem here is I've defined the space in the language of trees. So the width of my layers as I get closer to the input becomes larger and larger and larger. So the number of total variables in this neural network scales like m to the 2 capital L minus 1. So we get that the difference between the rate between Fm and F in L2 of P gets very slow in terms of parameters as the networks become deeper. I would like to remark this does not depend on the input dimension. So this is a curse of depth, not a curse of dimensionality. And for 3, 4, 5 layers, this might not be quite as bad, but it quickly becomes prohibitively bad. If we use a tree index structure, then this is a little bit better because we only need m to the L plus 1 elements. So we've got a lot of repetition, a lot of trivial elements in this system. So because of the index structure, it looks like we need more degrees of freedom than we really have, but still, this is not particularly good. And the question is, can we get around this? And that is, I think, possibly the most important open problem here, because normally if we look at a 2-layer neural network, that can be written as the expectation of something over a probability distribution. But if you look at deeper neural networks, typically we write things as the expectation of something, and the something is sigma composed with a conditional expectation. So we've got a lot of these conditional expectations here, and for every one of these conditional expectations, we can maybe get a Monte Carlo rate, but we really need a lot of parameters, and it's not quite clear whether we can reuse parameters or whether we need to set up new parameters all the time. So I think this is a big open question. How good can we make the rate in direct approximation? On the other hand, it means that every function in multi-layer space really can be approximated, never mind the rate. So any smaller function space would be missing something. Okay, and using this direct approximation theorem and using the Rademacher complexity estimate, we can show that if we look at some empirical risk functional, where we just compute the average loss on a data sample, and we add a regularizer which bounds the path norm proxy, then we, if our target function is in the correct space, if our target function is good enough, then the minimizer of this regularized empirical risk functional actually satisfies a good risk bound also in the limit, which goes to 0 as 1 over m and 1 over square root number of data samples. And you, just knowing this, you also know how large you should choose your penalty term. All right, so coming back to the question that was asked, we've got a whole scale of multi-layer spaces. And we know that the Rademacher complexity is not particularly large for any of them, in the sense that the Rademacher complexity, even if we've got a constant 2 to the L, goes to 0, like 1 over square root n. So we've got a quick decay of Rademacher complexity, a good rate. And that is going to mean that, to an extent, our function spaces are easily learnable, which means that they are not very good at approximating general functions. So if we've got a general Lipschitz function, then the rate of convergence as the multi-layer norm increases may become as bad as norm to the 2 over d minus 2. So in high dimensions, there exists a function which with Lipschitz constant 1, we can normalize it to have value 0 at 0, and yet we cannot approximate it well with neural networks of any depth, given that the path norm of these networks remains uniformly bounded independently of depth. So the question that was asked was, do these spaces get more expressive? Can we say something about that? And now I'm coming back to the structures theorem. So this is a theorem for neural networks with a single hidden layer. And so let F be in the one layer space. Then F is the infinite sum of infinitely many C1 functions. This sum is convergent, and these functions in the sum are C1 smooth, except on a lower dimensional affine subspace of Rd. So we know that the set where a neural network with a single hidden layer, even as width becomes infinite, is non-differentiable. That is a countable union of lower dimensional affine subspaces. In part, this is why I'm saying function representation is important, because you get this if you look at the representation of two-layer neural networks, and that you just do the calculation for two-layer neural networks and decompose this measure mu in a suitable way. So for example, the function from the distance function from the sphere has a curved singular set. It's non-differentiable on the entire sphere and at the origin. So this is not a Barron function. This cannot be exactly represented with an infinitely wide two-layer network, but this can be represented by a three-layer neural network because it is the composition of a neural network which gives us Euclidean norm of x, and a two-layer neural network which is just modulus z minus 1. You can come up with other examples. So you can take the maximum of some coordinates. You can take a function where the singular set is just, where two rays meet. So three-layer neural networks well, two hidden layers gives you a much more flexible structure already than this very rigid structure theorem for neural networks with one hidden layer allows. So at least in this particular case, we can say something, and for that we really need to dig into the function space structure for two-layer neural networks. Okay, so everything I've said so far was for neural networks which approximate something. So we've got an infinite width limit, which has a tree structure. But the tree index structure is really unrealistic. That's not what people do. People want to reuse the same parameters for different branches. And we've got networks. And for approximation theory, that did not really matter. But now we've got training. And there suddenly it matters whether a parameter is reused or not. So let's look at this normalization, which is more convenient to take the infinite width limit, because then we can assume that there is a non-trivial limiting object, whereas otherwise we would not get necessarily something non-trivial easily to describe in the limit. So we've got a finite neural network, which is this average sum, which is a composition of average sums. And very similar to the neuronal embeddings from the previous talk, we say, okay, we just generalize what an index set is here. This is a fundamentally indexed perspective. So we take probability spaces, and then we've got measurable functions on these, and we just set the representation of f with these weight functions now instead of discrete weights, as we've got a weight here for the lth layer, and the index il is generalized to a continuous or different index theta l, and then instead of the average sum over il minus 1, we've got an index space omega l minus 1, and so on and so on and so on. And the simplest index space, this integral is just the usual sum over parameters over the d+1 coordinates, because we have the weights, the bias absorbed into the d+1 coordinate. So this is just literally writing the same thing and making it slightly more general. But if all of our probability spaces are finite, this is literally the same thing. And now we consider function, we've got function representation, and we introduce a norm, again as the infimum, and again we multiply all the weights together and just integrate them over the product space. And the associated function class, I'm gonna say, is the set of all Lipschitz functions for which this representation norm is finite. And this obviously depends very much on the space, on the choice of probability spaces and by proxy probability measures. Because if we choose some finite probability spaces, then that is just the class of fully connected networks in which the lth layer has width number of elements in this finite set. So this is not a function space, not a linear space. However, if our probability spaces are just the unit interval and pi I is the Lebesgue measure on it, then A, this contains all finite fully connected neural networks, and B, it is a Banach space. And why does it contain all finite fully connected networks? That is because we can use step functions. And the only really important thing that I'm going to use about the unit interval is that if we've got, say, if we're given an M, we can easily chop it up into M disjoint sets. Each one has measure 1 over M. So this means that we can put step functions inside, and finite neural networks basically just correspond to step functions. But you can also take basically any other index set which has the same properties which you like better. So, you know, unit cube or Gaussian measure, or whatever you fancy. If then this is Lebesgue measure, and we just have one hidden layer, then this actually captures everything. Every Barron function can be represented in this form. Well, we've got just this one inner, we've got one nonlinearity and we've got one application, and just the unit interval is perfectly expressive enough to represent everything. But you could also choose a different probability measure. If then we choose, let's add one more hidden layer, then again, this contains all Barron functions. It contains the composition of a Barron function, so one hidden layer, and another Barron function. And in particular, this contains the absolute value of the positive part, the negative part of a Barron function. It contains pointwise maximum and minimum of two Barron functions, no more, but at least two. And it contains the product of two Barron functions. So everything that, all the examples that I said cannot be represented with one hidden layer, but can be represented with two, all of this applies to this space as well. So this is an infinitely wide neural network with two hidden layers, is seriously bigger than just one hidden layer.
Stephan, you have 10 more minutes.
Oh, I apologize. I didn't realize it was getting so late. So I'm going to say this space has measurable functions, measurable weights. So that is not a great space to do dynamics in possibly. And instead, we're going to talk about neural networks with more restrictive weights, namely Hilbert weights. So we assume that all the weights are in L2 of their respective domains. And then because we've got this index structure of a neural network, we rearrange the weights in this integral so that the two neighboring things don't share an index. And then we can use Hölder's inequality to see that because the indices don't share a weight, these two integrals, these two L2 norms, decompose into a product of L2 norms. So we get a smaller class of functions which we can represent with weights that have bigger regularity, namely L2. And we can take a functional representation here. And then if we've got this higher regularity, we can identify the weight space with a Bochner space of functions on 0, 1 with weights in L2. And so basically we could think of this possibly as particles in separable infinite dimensional Hilbert spaces. And I think this is a fruitful perspective, but this might tie more into what Hui said. And I'm just going to remark that we've got separable Hilbert spaces and all of these are isometric, but it does matter, for example, if you take little L2 or capital L2, because the coordinate-wise application of the nonlinearity is not invariant under taking isometries at all. And so we've got different function classes. The question of whether they are the same is not necessarily answered, but for the first space of multi-layer functions, the first hidden layer basically outputs a vector which is wide enough to contain the entire unit ball of Barron space. If we restrict this to an index structure of a neural network, then we at most output a vector which is wide enough to contain a separable subspace. And if we further restrict that, then we have a first hidden layer which only outputs something which lives in a reproducing kernel Hilbert space. So these index structures make it more restrictive. We can show that for Hilbert weights, these L2 norms grow at most like square root of 2, and I'm going to skip the proof, and it's really simple, just Hölder's inequality. But then we know that the multi-layer norm, that the path norm increases at most polynomially. So we know that we do not leave our function space particularly quickly. So I think this is also the right hypothesis class, the right norm for training. And the last thing that I'm going to say is the natural space when we've got these functions parameterized on L2 spaces is an L2 gradient flow, right? So this is another thing why the space of measurable functions might not be so good, but the space of L2 functions is really natural. And so we've got an L2 gradient flow, and if we just discretize this on the unit interval, we embed finite neural networks with step functions. And if we do that, we get that the evolution by the L2 gradient flow on the limiting space is exactly the same as the evolution of the weights across different layers with appropriate learning rates. So again, if we just look at the continuous model and discretize it appropriately, I think it gives us very instructive insight into what our training dynamics, what our finite model should be. Okay, and so we've introduced those function spaces, and I think they are related to training dynamics, but there's a lot of work to be done. Namely, we've listed a bunch of open problems, and I'm sorry that I slightly ran over time. And if there are any more questions, I'll be happy to answer them now. And as the last speaker, thank you so much to Chao and Song for hosting this lovely event, and to the other speakers for their great talks.
Thank you, Stephan. It's a nice talk. So there's a few minutes for questions. And actually, yeah, Jianfeng, perhaps you can just ask question through chat, through video. Yeah. So Jianfeng asked a question, not easy. So Jianfeng asked a question that the tree space seems much larger than the neural embedding space. Is that true? Can you categorize the difference?
So it's a really important question, I think. I think what we can show is that if we look at the function class which we defined in the beginning, the tree space, and then just the space which we've got where we've got measurable weights, if we take the unit ball in both spaces and take the L2 closure or uniform topology closure or whichever weak topology you like, then those are the same space. So in a sense, this tree space is a completion, assuming that we've got measurable weights. If we assume our weights to be L2, then, well, we can approximate the measurable function suitably well with L2 weights. So possibly the same thing holds, but whether the L2 norms remain appropriately bounded is a good question. And I think it's difficult to say I'm not sure whether we've got enough degrees of freedom to appropriately reparameterize things. And let me see whether I've got something here. Yes. So if we look at something which has finite path norm, so let's say that it lives on the unit sphere, then the just two hidden layers. So the outer coefficient would be 1. The innermost layer would be some constant vector. And then the intermediate layer we set to be BST, which is f of s minus t. So the path norm remains perfectly reasonably bounded for this, no matter what we do. But if this function on the intermediate index set is just L1, but not L2 integrable on the unit square, on the unit interval, then the path norm is finite, but we can't really use all our easy degrees of freedom to bound this product of L2 norms in a good sense. So, especially because of this singularity along the diagonal. Obviously, there are a lot more degrees of freedom possibly, and we can rearrange index sets, and the map from weights to realization is non-injective. So it is really hard to say what exactly the relationship is there. And I think you've got, what we can say is this heuristic. So the path space outputs everything in Barron space. And the smallest of the spaces has an inner layer which can output everything in some RKHS. So the same RKHS. Obviously, your RKHS can be pretty dense. So and the smallest space is still large enough to contain all Barron functions, compositions of Barron functions. Every easy example that you can think of is still in this smallest space, at least in the case of two hidden layers. So it's really hard to come up with an example of a function that is in the path space, but not in the arbitrarily wide space with Hilbert weights. And my conjecture is that this space is significantly smaller, but I don't have a proof available yet.
Yeah, thank you for your answer. I have a quick clarification question. So you went a little bit fast in the last part about like training, relationship to training. It seems that in the training part, your result is that the norm doesn't grow very fast. Is it?
Yes. So I knew that there were many more works about training that 3 of which were presented today. And so what I was interested in is the hypothesis class for neural networks. And so I think what all I wanted to show was that if we look at our model for arbitrarily wide neural networks, we can recover normal training dynamics, and we show that the norm does not increase particularly fast. So we can show that the hypothesis space that we describe is very reasonable under neural network training. But obviously, there are many different training algorithms, and so the description of the hypothesis class does not really depend on training. It's more of a sanity check that the hypothesis class that we describe actually has some practical relevance, that not only do we understand the learning and the generalization for this hypothesis class, but also that commonly used training algorithms play nicely together with our function space.
Thank you. Are there any more questions?
Can I make a remark?
Yes,
Hello?
please.
Yeah. So in the first 3 talks, people speak about mean field limit. I have a mixed feeling about this terminology, mean field limit, because if you look at 2-layer neural networks, you know, the work that you have done, you know, Eric and everybody else done, writing down the mean field equation. That equation is satisfied for the finite neuron system. You don't need to take a limit. Now, in today's exam, first 3 examples, it seems like everybody needs to take the limit, but I'm not sure that's intrinsic. For example, the example Stephan just showed, you don't need to take limit either. You can just discretize, or the same equation is satisfied if you just define the appropriate functions. The equation is satisfied by finite neuron systems also. So I wonder, you know, I'm not exactly sure that all these mean field equations or continuous equations are equivalent. So I wonder in the previous examples whether the limit equations are indeed satisfied by a finite system. Certainly for the 3rd talk, because it was talking about SGD, so if you talk about SGD, then it's not good. But if you do GD, I wonder whether the equation would be satisfied by a finite neuron system.
Yeah, Hui or
yes, right. Yes, I think so. If we don't do SGD, but we do gradient descent in continuous time for the finite system, then the limit equation I wrote exactly recovers the dynamics of the finite system, discretized system.
So you don't need to take a limit.
Yeah, so I would not need to take a limit. Essentially,
okay.
Yeah.
That's yeah. But it seemed like the second talk, the limited system for the second talk seemed to be quite essentially different from the rest. It seemed, my impression is that the first talk, third talk, and fourth talk, the limit equation might be exactly the same thing, but the second talk might be different. Anyway, the speaker's left, so he can't answer the question. So, but I'm just, my view, my comment is that it really mean field limit is not necessarily the best terminology here. It's really the mean field scaling. That's really essential, that you have the 1/m factor in front of the sum.
Yes, so I may possibly say something about this. Our training dynamics, I skipped over this fairly quickly. What I showed was that these L2 norms don't increase particularly fast in time. But in ReLU networks, what we've got is scaling invariance. We can put we can just put very small weights in one layer and very large weights in another layer. And possibly the really important thing is that we take this 1/m and then we put the weights in all the layers to be of similar order of magnitude, no matter the width. So if the initial condition is reasonable here, then we've got this square root t growth. But obviously, if the initial condition is very large in some layer, I think that is when we would start to see very different behavior, and that is possibly when we get to the neural tangent kernel limit, when just the coefficients scale poorly. So I think that is when we would start approaching that by discretizing the finite system in this framework.
Can I add a quick remark? So, so I think this limit thing. So in the first two talks, we encounter IID initialization, and I think with finite discretization, it's hard to realize that something is exactly IID. So in the third talk, what we did is this more general embedding scheme, and this embedding scheme can allow for essentially arbitrary initializations put on it. So in particular, or any kind of discretization that we want to place on it. And so that will allow us to exactly just recover what happens in the finite case. But in the case of IID, I think if we take empirical distribution of a finite network sample from IID, that distribution of weight is not exactly IID. So.
Well, IID is a special initialization. It's the dynamics that we're mainly interested in. In the first work only look at the special initialization, so it's difficult to say what the general dynamics is. But the second talk wasn't. The second talk derived the general dynamics, which seem not to be true for the finite neuron case. So that's different from the rest of the other, the others.
So I had the impression that the second talk was deriving the dynamics, but it was using properties of the IID, but maybe that's not crucial there. But yeah, I'm not sure if it will apply for the finite neuron dynamics.
I have a question maybe related with this. So that, from the first talk, and we see that if we start with IID sampling and the dynamics never leave it, right? So that it's, in the end of the day, we get a product measure. While the Hui's talk, I think, deal with a more general space, and the last one, even larger space, it seems. So it seems there was a hierarchy of like what you initialize and what kind of dynamics so that which function space we should use. This seems to be very different from like the traditional function analysis point of view, right? Because when we consider approximation, we would never think about the dynamics. I wonder whether, the speakers could kind of comment on these, or like what is the right space to use I mean, for combining all the results like approximation, generalization, and training?
So I think the big problem is that traditional functional analysis, you've got PDEs which naturally respect those linear spaces. But the training dynamics in neural networks is different. You do not train a function, you train the weights of a function, and the map from weights to realization is complicated. So there's a lot of non-linearity in here, and I think I think it has a different flavor from the traditional functional analysis approach in that sense, and it's entirely possible that the same function spaces are not exactly the right objects for everything, because I like to, so let's go back to the analogy of the of approximation theory, where we say that finite neural networks are the same as polynomials because they have finitely many coefficients. Then if I take a norm bound and I take a closure, then I get these path spaces, which are something like a Sobolev or Bazov space in a sense, as a generalization. And then I'm looking at training dynamics, but for training dynamics, suddenly I really need to look at the weights, and I really need to look at a weight structure. So I need my weights suddenly to have meaning again, which polynomial coefficients, Taylor expansions don't work in Sobolev spaces. So maybe this is more like a CK space or an analytic space, where actually the coefficients of a polynomial make sense. So, and I think the dynamics really lives on something like this. At least that is my idea, and we might have a different perspective.
Well, I think it's for two-layer neural networks, everything seems to come together quite well.
Yes.
So for right now, for multi-layer, more than two, it's true that there are still gaps, but I wouldn't say there is already evidence that for multi-layers, the situation is essentially different.
It's true. It's true. I think there is a lot still that we don't understand, and for two layers, because we go from something finite to something infinite to something finite. For more hidden layers, we need to have cross connections between very possibly uncountable things, and that seems to change the situation, at least the description a little bit, and make it not quite as accessible. I think we've described the correct function classes. It remains to be seen a little bit how different they are, and whether we can show, for example, that they are the same thing.
Maybe a naive question. So that for the third talk, right, using this neural embedding technique, can one, so is that actually just corresponds to exactly this this X omega space that is defined here? And can we endow a norm to these things and talk about approximation? Just trying to make sure I understand the results.
Yeah, so I just very briefly mentioned it, but I think it's true, right, Stephan? It's that it's the same space as the X space that is equipped here. But because I was only interested in dynamics, I didn't put any norm on that space. But as we can see here, if we want to put an approximation viewpoint on it, then we can equip it with norms, and perhaps different norms as we see here. Either there's a L2 or other norms that we can place on it, and there will be different structures that come out of it. But yeah, but as Stephan said, these things can be to get studied together with the dynamics, right? So if we start with initialization that is in L2, then perhaps the L2 view, that the L2 norm only evolves so much, and perhaps it makes sense in that case to put that norm.
So I think roughly the same thing. I believe that possibly depending on whether the weights are assumed to be measurable or square integrable, or I think there is still a bit of variation, but especially since the weights were usually in Hilbert spaces, I think the natural comparison would be this L2, and then possibly there would be more of an interpretation in the third talk for this Bochner space where the weights are L2 with values in L2. But the problem I had with this smallest space was to put a norm on it, because obviously it's a subset of a larger space. It is a linear space, and I can just look at the restriction of the path norm. But that was not the natural thing that occurred to me. So because that does not necessarily control the L2 norms, so that would not necessarily be a Banach space. So instead, I put this product of L2 norms on it, which controls the path norm, and which is what we look at in the dynamics and show that it doesn't grow particularly fast. But if you look at that, that's not a norm. So so I'm not sure. It is a linear space, but I'm not sure what the right norm to look at on this smallest set would be. And the problem with making it a norm is not necessarily the scaling. That's fine. You can multiply